Hey, what's up everyone? Welcome back to the channel. So this particular video is about the problem Kth Ancestor in a tree. Now this problem is a standard DSA problem guys, and in this video I'll talk about two interesting approaches to solve the problem. So guys, make sure you watch this video till the end. Now the problem statement says that you are given a binary tree of size n, a node and a positive integer k. Your task is to complete the function Kth Ancestor. The function should return the Kth ancestor of the given node in a binary tree, and if there doesn't exist any ancestor, then return -1, right? So see, talking about the ancestor, so we all have our parents as our first ancestor, right? After this we have our grandparents, then we have our great grandparents, so like this. So finding ancestor basically means moving upward in the family hierarchy, right? So once you have understood this, you are good to talk about this example. The example says that we are given a node 4 and this whole tree, right? And we have to find the second ancestor. So see, the first ancestor of the node 4 is this node, right, which is the parent, and after this we have the second ancestor as the node 1. So 1 is going to be the output for this particular example, right? Now one more note is given here. It is guaranteed that the node always exists in the tree, right? So now I hope you guys have understood the problem statement. So let's talk about the solution, guys. Okay, so I have written one example here, and for this example the value of node is equal to 9 right here, and the value of k is equal to 2, right? So I have to find the second ancestor of this node 9. So the first approach that comes to my mind is very simple and straightforward. I can start with this node, and then this node is going to ask it who's my parent. So 5 is the parent, right? So 5 is nothing but the first ancestor of this node 9. Makes sense till now? Okay, then this 5 is going to ask who's my parent, then 3 is the parent, right? So 3 is nothing but the second ancestor of this node 9, right? Once you have understood this, your task is done. See, we are going to move to upward direction again and again till we have found the kth ancestor, right? So in order to verify that or in order to make sure that this is the kth ancestor, I'll start with k equals to 2. I'll keep decreasing the value of k, right? So the value of k is 2 here. For this, the value of k will become 2 minus 1, which is 1, and at this point the value of k will become 0, right? And the moment the value of k becomes 0, at this point I can say that current node is my answer, right? So let me try to write the pseudocode. So it's simple. While my k is not equal to 0, so k is not equal to 0, I'll simply do k minus minus again and again, and along with this I'll also do, so initially let's say my node is equal to 9, right? So my node is equal to 9. So I'll say that now my node is nothing but the parent of itself. So parent of, or I'll say get parent, right? So I'll say get parent of the current node. So this line, what this line will do is, this line will say, okay, now the value of node, initially the value of node is equal to 9. Now the value of node will become 5, right? After this, the value of node will become 3. So the value of node is going to change again and again till my k becomes equal to 0. The moment k becomes equal to 0, node is storing the answer. So simply return node, right? Node. This is how we can solve the problem. But there is one more case to handle, and that particular case is, let's say my node value is equal to 3, right? And for the node 3, I have to find the second ancestor. So I'll start with this point. I'll say that, okay, what is the parent of this node? The parent is nothing but this one, right? And what is the parent of this one? There is no any parent. This is where I can face problem while finding the parent, right? It can return me a null node. So I have to verify that as well. I'll write in the while condition, while my k is not equal to 0 and my node is not null. So I have to make sure that the parent exists, right? So if parent exists and my k is not equal to 0. So now there are two conditions when our while loop is going to break. Either my k equal to 0 or the parent doesn't exist. So if the parent doesn't exist, in that case I have to return -1, right? So this return statement is again going to change. It will say that, okay, if parent exists, right, only in that case I can simply return node, right? Else if the parent doesn't exist, I'll return -1. So even this is given in the problem statement itself, right? The problem statement is saying that if there doesn't exist any ancestor, then return -1, right? So this is what we have to handle in this particular code. Now the question is how to get the parent, right? This is very important question, guys, and the way we get parent is used in multiple kind of problems, so it's an important concept. The first approach that you can say is we can find the parent using a recursive approach, right? And it is going to cause O of n complexity. So this way the total complexity will be O of n into k, right? We are doing O of n task k times. So this is going to cause time limit, like it is not considered to be a good complexity, right? O of n cross k, where it is not going to work for large inputs, or we need a high processor to work for large inputs, right? I hope that makes sense to you. So what we can do is we are going to optimize this approach. We are going to reduce this approach to O of n, right? Just we need to get a way so that we can get these parent in O of 1, and the only way to do this is store parent somewhere, right? So if I have stored the parent of every node in an array, then I can simply access the nodes, right? Then so this statement will change now. This statement will say that okay, let's say I have stored every parent in the maps, right? So I'll say that map.get node, right? And this is going to give me the parent in just O of 1. So this is what the optimization is. So now the complexity of this particular approach is O of k, and the complexity of right finding the parent is O of n, right? Because we need to traverse every like node, and then we have to store the parent. So now let's see how we can find the parent. Okay, so now the question is how to get the parent of each node. So after this only we are going to complete the approach one. So see, in order to get the parent, I need a function. Let's say I have a function which is parent, right? And this function is going to take the current root. So I have a current root. After this I need uh, -1 as the current parent, right? Because the parent of this root is nothing but -1, so I'll initially have -1. After this only what I'll do is I'll pass a map as well. So because I need to store the parent somewhere in a map, right? So let's say this -1 is a variable which is parent. So parent is initially storing -1. After this I'll go to this node. I'll say that, and while I go to this node, then I'll make sure that now the parent is equal to like 1, right? So how to do this? I'll simply say that call the same function. This is a function, right? So this is a recursive kind of approach because I need to traverse every possible node. So I'll say that parent root dot left, and see, initially the parent was -1. Now the parent is nothing but root data, right? I hope that makes sense to you. Now my parent is nothing but the data of root. So initially the data of root was 1. So the parent of this 2 is nothing but 1. Similarly, the parent of this 3 is nothing but 1, right? So I'll again call the function for write node as well. So it will say that, okay, root dot write, and I'll say that root dot data is the parent, right? For write children as well, because both are the children of the same node. And see, along with this, I have to pass the map as well. So this is how we can get every possible node, right? And see, in recursive approach, we need to call a like we need to write a base condition as well, so that we have to stop somewhere, right? So if my root is equal to null, I'll simply say that return, right? Okay, now what's special about this function is this function is going to check out every possible node, and in every call I will have two important things. First one is the root, and the second one is the parent of the root. So I can store the parent. I'll say that, okay, now my map is basically going to tell me the parent, right? So parent of current root is equal to nothing but this parent, right? Parent variable. So this is how I can get the parent of every node. So when this function completes, I'll have every parent stored in a map. So for this I can say that the parent of 1 is equal to -1, right? After this I'll come to this node, then I'll say that, okay, the parent of 2 is equal to 1. After this I'll come to this function, right? And now my parent is 2 because I'm passing the root dot data. So now my parent is 2. I'll say that, okay, parent of 4 is equal to 2. Similarly, I'll come here as well. So the parent of 5 is nothing but 2, right? This way I can store the parent of every node. So I'll say that, okay, the parent of 3 is nothing but 1, because see, I have 1 here. Then when I call the function parent for this one, then I'll pass 3 as well, right? Because 3 is the current root. So I'll say that, okay, the parent of 7 is 3, and similarly the parent of 6 is equal to 3. So this way I can have every parent. Now I can access the parent in this particular like from in this particular code in just O of 1 time, right? So this way I can write my first approach. And the complexity, talking about the complexity, so the time complexity is, see, we are traversing not more than n nodes, right? And we have k as well, so k is always smaller than n. K is always smaller than n, right? So I can say that the complexity is nothing but O of n, right? This is time complexity. What about space complexity? So the space complexity is, again, see, we are storing the parent of every node. So we can simply say that space complexity is again O of n. So this is the first approach. Let me show you the code quickly. Okay, so this is the code, right? You can see here that this is the main approach that we need to follow, and before following this approach we need to store the parent somewhere, right? So I have this unordered map which is parent map, and I'm storing the parents here, right? Similarly, I have written the same code in Java as well, right? And I have written the code in Python as well. So this is how we can write our first approach. But now I'll talk about the problem with this approach, and after this I'll talk about the optimization that we can do, right? So first of all, let's talk about the problem with this approach. See, the problem that we have is we are storing the parent of every node, right? But while traversing, we don't need the parent of every node. Let's say the given node is, so see, for this example, the given node is 9, right? So we need the parent of 9, which is 5. Then we need the parent of 5, which is 3, right? So this way we can get our answer. But the question is why we are storing the parent of these nodes, right? Because we are not sure about what nodes we have to traverse. So this is the problem that we have with this approach, right? So the complexity is O of n here, space complexity, right? So second approach is just about space optimization, how we can reduce this particular complexity to O of h, right? And now the second approach is very interesting and important as well, because this is used in like very interesting problems like finding the nodes at distance k. This is one of the application of the second approach, right? So now let's talk about the second approach. Okay, so th this is where I'll explain the second approach. It's based on recursion actually, right? So let me start. Guys, the idea behind this particular approach is to search for the given node in the whole tree, right? Starting from the root node. And while searching, I want to get the distance of the given node from the current node from where I'm searching, right? So let's say at any point in time I'm searching from this particular node. So I'll say that, okay, I have got my distance as 2, right? And see, the distance is 2. This means that this is the kth ancestor or the second ancestor of the given node. So that's how I can get 3 as my answer, right? So now let me show the same using the dry run so that you can have a better understanding of the approach, right? So I'm going to start from the root node, and see, till now root node have no any idea about where the node 9 is. So it is going to ask from the left child and the right child, right? So see, left child and right child again doesn't have any idea about the node 9, so they are going to ask from their children's. So now you can see that this 4 again doesn't have any idea, so it is going to ask from this node 7, right? And node 7 doesn't have any child, so it will say that there is no any node which has the value 9, so it will return -1, which means that not found, right? So it is going to return -1, so it will have -1, right, from the right child, and there is no any left child, so again it will say that there is no any node, right? So it will return -1 again. After this I'll come to this node, and the moment I come to this node, so there is no any right child, there is only left child, so it will say that okay, there is no any node which has the value 9. So at this point I can say that the node 9 doesn't exist in the left subtree. Make sense till now? Now what about the right subtree? So for the right subtree, see, last time I called for these two values. So now for this 6, it doesn't have any idea about the node 9, so it is going to ask from its children, right? Then this 10 doesn't have any idea about node 9, and see, it doesn't have any children as well, so it will say that node 9 doesn't exist, right? So it is going to return -1. Then this 6 is again going to return -1. What about this 5? This 5 has left and right child. The left child will say that there is no any node 9, so it will return -1. What about this 9? This 9 will say that I am the node 9, right? So the distance of me from myself is 0. I need the distance as well, remember guys, right? So now I'll come to this node 5, and I'll see that node 8 is saying that there is no any node, and node 9 is saying that there is a node which is at distance 0, right? So this particular node will say that okay, if it is at distance 0 from node 9, so it will be at distance 0 plus 1, which is d plus 1 from me, which is the distance 1, right? And even it makes sense because these two nodes are at distance 1. So whatever is the distance of node 9 from this node, it is going to increment by 1, right? So now the distance of 5 from node 9 is 1. What about this 3? So this 3 is going to get two outputs, one from the right child and second from the left child. So the right child is saying that there is no any node 9, and the left child is saying that node 9 is at distance 1. So this 3 will say that, okay, if the node 9 is at distance 1 from you, then it will be at distance d plus 1, which is 2 from me. Make sense, right? So this is very important point, guys. At this point you can see that d plus 1 is nothing but equal to k, right? So this means that this 3 is going to be the output, right? Why? Because this 3 is the kth ancestor of this node 9. So I'll say that answer equal to root dot data. I hope you have understood this particular thing, right, guys? This is the main approach. After this, I'll come to this one, and at this one, I'll say that, okay, if the node 9 is at distance 2 from this node 3, then it will be at distance 3 from the node like 1, right? So this is how we can solve the problem. See, we have just traversed the this particular tree one time, right? So now the question is how to implement this. First of all, let me erase this, and now I'm going to write the code, right? But first of all, let me make this grid smaller. So okay, now see what I have. First of all, I'll write a function which is an ordinary search function. So I'll say that uh, okay, let me change the color now. So I have a function which is search, and this function is going to take two parameters. The first one is root and the second one is the node, right? Okay, and this is going to be an ordinary search function like how we search values in a tree. So the first condition is if my root is equal to null. So I'll say that if my root is equal to null, in that case I can say that not found. So let's represent not found with the value -1. So it is going to return -1. What about the found? So let's say if my root dot data is equal to -1, okay, is equal to node data, right? So in this case we are simply going to return 0, right? This means that the moment I got my node, so I'll return 0. You can see here we have returned 0, right? Okay, after this, now you can see here that if these two conditions are not true, then this is the case, right? For the node 1, I have to ask from the left and right child. So I'll say that my int left distance is equal to, why I'm writing left distance, let's say since this is an ordinary function, so let's say L is my left, the result of left subtree, right? This was -1 for this subtree, you can see here, right? So let's say L is the result. I'll say that search uh, on root dot left, right, and node. This is what I need to write. After this, what about the right distance? So I'll say that if right, then I have to search for uh, root dot right. This way I can get my result, like whether the node exists on the left subtree or right subtree. Now there are two possibilities: either the node exists in left subtree or in right subtree or in no any of these subtrees, right? But there is no any possibility that the node is found on both subtrees. And even it makes sense because there is only one instance of the node present in the tree, right? So now let me handle all the cases. So how to handle these cases? I'm simply going to write one condition. Let me use green color. So I'll say that if my left is equal to -1, okay, left is uh, let me write if my left is equal to not -1, right, and my right is equal to -1. This means that the node is found on the left side, right? So this is for the left side. I'll simply return 0, and else if my left is equal to -1 and my right is not equal to -1, right? So for this I'll again return 0 because the node is found, and if none of these condition is true, in that case I have to return -1, right? So I'll say that return -1. Okay, let me remove this step. I want to write it more clearer. So I'll simply write return 0 here. Now you can ask me a question that why I'm writing these two things in a separate condition if both are returning the same stuff, right? There is a reason. I want to separate the left part and the right part. This part basically means that the node is found on the left subtree, and the below part basically means that the node is found in the right subtree. I hope that makes sense to you, right? And I'll use these things definitely. So let's say if the node is found on the left subtree, so this L is basically representing the distance, right? See, in order to get the distance, I need to return d plus 1. because we have written d plus 1, right? Because let's say that distance is 0 for this, so d plus 1, which is 1 for this particular node, right? So I'll say that, okay, if my node is present on the left side, then I'll return L plus 1, right? I'm using black color in order to show you the modification. Okay, even let me use the red color in order to show you what modification we need to do, right? So I'll return L plus 1. I'm returning L plus 1 because L is representing the distance, because it's not equal to minus 1, and L plus 1 basically means the new distance, right? For this, the distance is being represented by R, so I'll return R plus 1, right? And before returning the distance, I need to do one more thing. If my R plus 1 is equal to K, right? This is the condition. Like you can see here, we have got one condition true here. If my distance plus 1 is equal to K, then I can say that my answer equal to root dot data, right? I hope that makes sense to you. Similarly, I can write here as well. So I'll write if my, okay, what should I write? I should write if my left plus 1 is equal to K, then I can do the same stuff, right? Answer equal to root dot data. This is how I can solve the problem. Now you can see that I have modified the function in order to get my answer, right? So this is how we do an implementation of an idea. Once you have understood this, I can show you the code. So this is the code, guys. You can see here that I am storing the like solution in an answer variable, right? And we are passing the address. This is call by reference. If I want my change to be reflected outside the function, then I have to use call by reference, guys, right? There's a pointer, then I'm just going to modify the value in the pointer, and see, this is the function which is same as the function that I have written, right? And you can see here that instead of writing L and R, I am using a full left search and right search, right? And now I have changed the function name as well, which is now solve instead of search, because this makes more sense here. And this is the Java code, guys. Again, in the Java code, there is a little bit of difference, which is we don't have any pointers in Java, right? So we are using an array here. Array is basically going to implement the call by reference in Java, right? So because any change in this array variable is going to be reflected in this particular function, and same in the Python code as well. In the Python code, we are using Python list, right? So this is all about this video, guys. First, now let me talk about the time complexity. So talking about the complexity analysis, so let me start from the time complexity. The time complexity of this function is O of n, right? Because I have shown you the dry run as well. I'm not using more than n nodes, right? And the space complexity is equal to O of h, guys, because I'm storing values which is actually used by recursion stack, right? So recursion stack is not going to store these much of node at a time, right? So this is nothing but O of h, right? So this is recursion stack space. Now this is all about this video. I hope you guys will like the explanation. Thank you.